All right, so I'd like to talk about standard F.2.e, which is standard 118. And in it, it talks about determining the period for systems involving series or parallel combinations of identical springs. So first, let's talk about what that means. For series springs, that just means two springs like in a row. So you hang a mass and both strings are hanging in a line. And for parallel, think of parallel lines. It's two springs side by side. So let's talk about the series springs first. And for series springs, I'll recall that the spring force is Kx. Since both of these springs are going to stretch some distance x, then the whole thing would stretch twice as much. But the F doesn't change. Whatever mass you had, it's the same force pulling down. So if it stretches twice as much, then K has to be half K to keep the Kx the same value. In general with this, what we would do to solve this is 1 over K equals 1 over K1 plus 1 over K2. So an example, if both springs have a K of 3 newtons per meter, we would have 1 over K is 1/3 plus 1/3, which means 1 over K is 2/3, or K is 3/2. We just flip both of those, and we get K to be 1.5 newtons per meter. Now let's take a look at the parallel springs. With parallel springs, two springs working together, they're going to just pull half as much. So if they each pull half the distance, then K must be twice the K value. So in general, the way we solve for this is K equals K1 plus K2. For an example, if K again is 3 newtons per meter, we have K equals 3 plus 3 equals 6. So the main thing that we need to recall here as we go through with this is that if we have series springs, we need to do the inverse addition. 1 over K equals 1 over K1 plus 1 over K2. And for parallel springs, we just add the K values together. K equals K1 plus K2. It also talks about springs of different lengths in this. So when we look at this, think if we have a spring maybe of some length, maybe one a little bit longer, one even longer. The example I'm going to talk about is what if we just cut one of these in half? So we have half the length of the original spring. Well, if we cut it in half, the top part is only going to stretch half of what the original part did. So when we look at that, again, remember that F equals Kx. And if I have some mass hanging on here, it's the same mass. So it's not going to change, which means that the left side needs to stay the same. So that means if X goes to X over 2, it's going to stretch half as much. Then K goes to twice the K. So in general, again, we could say for a given spring, Kx1 equals K2x2. So remember, if we have some spring, K1x1 equals K2x2. So let's take a look at a couple examples. See if you can figure these out. First, let's do one. If I put a 3 newton meter spring in parallel with a 5 newton meter spring, what would my new K value be? Well, these are in parallel, so I just add them together. 3 plus 5 is 8 newtons per meter. Let's look at one in series. What if I put a 4 newton meter spring in series with a 2 newton per meter spring? Well, I put these two in series. I need to do the reciprocal addition. 1 over K equals 1 over K1 plus 1 over K2, which is 1/4 plus 1/2, which is 1/4 plus 2/4, which is 3/4. So 1 over K is 3/4. I flip both of those and I get K is 4/3 Newton per meter. Now let's look at one if I cut a spring into 3 equal parts. So what was the new K value now? Remember that K1x1 equals K2x2. X2 is now 1/3 x1. So I do this and I can multiply both sides by 3 and I find out that K2 equals 3 K1. You might be saying, oh, that's great. We can now find K. But the standard says find the period. Remember to do that the period is 2 pi over omega. And if we have a mass on a spring, we can start with the sum of the forces equals ma. And we know that the spring force is minus kx equals ma. So A is minus k over m times x. And this follows the idea of A equals minus omega squared x, which is the form of simple harmonic motion. So omega squared is k over m, or omega is the square root of k over m. we put that back into our period equation, and we have the period is 2 pi over the square root of k over m. But to get that radical out of the denominator, I just flip it, and I have the period is 2 pi square root m over k. So once we find the k values, as talked about earlier, we can then go ahead and find out what the period of that spring is.